So this is the schematic diagram for the project of medical devices. I print this out. So based on this, I'll be patching this circuit, so which I've already patched. So I'll be using the oscilloscope here to show the frequencies, and then to generate the sine wave, I'll be using this function generator at the setting of 100 Hz and 200 millivolt peak to peak, and I'll be getting the power source from here, from this power source thing, at 9 volts. I'm planning to use the 9 volts to power up my circuit here. So what I basically did on my circuit is, since there is an audio jack here and there's some components here as well, I'm planning to cut this off and start to do the patching from C1, which is a capacitor, which I've started here. So from capacitor it will be connected to the first op amp, operational amplifier, which is a TL072 to pin 3. This will be my first test point, which approximately will be here. Yes, will be here. This is my first test point, TP1. My second test point, however, will be at TP2, which is set for using the first pin at between C4 and R4. So that will be basically somewhere around this place, Yep, because this is the exact line we have here. It is somewhere around this place. So this is the basic, yep, somewhere around this place. So that'll be TP2, and TP3 is behind an capacitor, so it should be here. Around here. I mean, it should be here. So it'll be, should be here. And TP4 will be here, and TP5 should be here. So in this case, right, TP4 and TP5 will not have a solid graph because the graph is not readable. So I will explain the graphs on a paper with a passband graph. Yeah, with all the bandwidth and everything, it will be explained. So this is the basic outline on what I am going to do for the project and the patching. What I did for the patching and the project. Okay, so this is my circuit here. So let me briefly explain on what I did here on my circuit. This is my ground, this is my VCC. My probe is connected to the point where I'm testing it, which is at TP2, and my ground here is connected to the ground of the probe, the function generator's ground, and the ground from my power source. This power source is 9 volts. So I've connected it here to my VCC ground. As you can see, I've connected 3 pins here also. So I obtained this waveform, which is sine wave, which has 4.6 divisions at 2 volts per division. So 4.6 divided by 0.2, I get 23. So the waveform here is obtained from the function generator here at the setting of 100 Hz at 200 millivolt per peak to peak. this is my TP3. What I done was, since the testing point is here for TP2, I just shifted the probe from TP2 to TP3, which is here. So I shifted the probe here, and my waveform turned out to be square waves. Yep, turned out to be square waves. So everything, all the settings are still the same, even the function generator is still the same. So everything's literally the same. It's just that I am using different testing points. So this is testing point 3. So since I've connected, this is my waveform now. So since I connected my circuit to this trimmer, I'll be changing I'll be testing out the trimmer to see if there'll be any changes on the graph. So let's go clockwise. No changes. Okay, I'm going anti-clockwise now. So when I've turned it completely to anti-clockwise, there are no any graphs here. So when I open a little bit by little bit, I can see the graph again. So hello, this is the schematic diagram of my medical electronics project. So this is the diagram which should be acquiring sound output, for example like heartbeat, and it's supposed to process the sound. This is supposed to be a biomedical sound processing system. So let's see this in detail. So I am demonstrating here stage 1, theoretically explaining what are we looking at. So stage 1, which is up to this point before this TP2, that is stage 1. So stage 1 is dual low noise JFET input general purpose operational amplifier, which is built with IC1, which is TL072, which theoretically has voltage gain between 10 millivolts and 1 volt, but no current. So for those who don't know, JFET is junction field effect transistor. Okay, so op-amp amplifies sound where subtle shades in the character of sound can be added or subtracted. Circuit brings the signal from an electret microphone up to a suitable level for line input, which is basically how this stage 1 actually works. And not the stage 1, but the whole circuit works. So let's see part by part. Let's break down the first stage part by part. C1 is a 10 microfarad capacitor, which blocks DC bias voltage from input. So, and as you can see, the circuit down here, which is made by two resistors, 10k resistors, which is R6 and R5, is a voltage divider. It's a voltage divider circuit. So this voltage divider provides half of the supply voltage, which enables the op-amp to be working at a single power supply mode at 4.5 volt. So that's up to that point you can have the test point 1. So this is the TL072 IC. This one is connected to VCC and this one to the ground. This pin, the C1, is connected to the third pin of the TL072, and this is the passband filter circuit. Is connected to coming from the second pin and going up to the first pin. Okay, so let's see it in detail. So at this point of the part of the circuit, we have 222k resistor and 682 picofarad capacitor and 10k resistor, and we have C3, another capacitor with 1 microfarad. So this is a fixed gain closed loop non-inverting op-amp for this part only. Okay, so R2, R3 and C2, C3 form band pass filter. So this is a band pass filter. Okay, pass band gain is 222 over 10k, which is 222 divided by 10k plus 1 will be 23, which is basically the which is calculated by the with the formula of R2 divided by R3 plus 1 is equal to the pass band gain, which is in our case it's 23. Okay, so what we have another C4 here. What is the main purpose of this C4? This passes AC signal on while blocking DC signal. Is a coupling capacitor. This coupling capacitor couples the output from the first amplitude to cut the output waveform. So that's basically it for the first part. Okay, so to read the waveform here, I've actually get some data to draw the graph in the passband graph. So this is the data. So this is all data. As you can see, up to the 500 point, the V out is actually increasing, and after the 500th point, the V out is actually gradually decreasing, and the gain is VO to V in is increasing until 500 until 100, and it's decreasing gradually from 500 onwards, and same goes here. Okay, for this part it's actually increasing until 100 as well, and it's decreasing from 500 onwards to all the way to 69. So I've got the graph for this. I've drawn the graph for this, and this is the low pass band. This is the cutoff frequency here, which is obtained by minusing 3 dB from the peak point. Okay, so we are getting 300 hertz here. This is the low frequency, and this is the high frequency, and this is the formula. To calculate the bandwidth, we have to actually minus the FH minus FL, which is high frequency minus low frequency, which we end up with 170 hertz. So that's all for this part, stage 1 explanation. Okay, so now we are looking at stage 2, which is from this point, which is basically this part. Yeah, this is the stage 2 circuit of this medical device project. Stage 2 circuit. So what are we looking here is a negative feedback loop amplifier. Okay, which shares the same IC TL072, yeah, which shares the same IC1. These both are the same ICs. Okay, so how does a negative feedback loop actually works? How does it actually is? So this is a example of negative feedback path. So as you can see, this negative feedback path is connected to the negative to the negative side of the op amp. So it is connected like this and connected to the V out, as in the V in is coming from a single source from outside here to the positive side of the op amp. Okay, so what is the negative feedback in generally what's the negative feedback? A process where a portion of the output voltage of the amplifier is returned to the input with an inverted phase of 180 degree, which is 180 degree out of phase. Okay, so this is the negative feedback, and let's see in whole. As you can see, we have a trimmer here. It's a 100k trimmer. Okay, what does the trimmer does in this particular circuit? So it controls the feedback signal, which can reduce the overall gain of the amplifier, which can function as a linear amplifier. So this trimmer here can reduce overall gain of the amplifier and also will function as a linear amplifier. Okay, now here we have a voltage divider here as well. So it is made out of two 10k resistors, which is R9 and R10 is connected to R5. Okay, so this voltage divider circuit is quite a special circuit because it has two functions here. So it provides and it enables the op-amp to work at single supply mode, and also it acts as a level shifter so that the output will not be clipped. So this is a level shifter. At the same time, it enables the whole circuit, this part of the circuit, whole circuit, to work at a single supply mode. So that is all basically for stage 2. Okay, so now we are looking at stage 3. This stage 3 uses a second IC, which is a TL072. It's another IC too. So IC2A, second IC is IC TL072. This patching way is patched as a Salon key second order low pass filter. Okay, so let's see this part by part. C5 here is a 10 microfarad capacitor which blocks out DC and allows AC signal to pass through. So you can see here, this is a voltage divider. So it also it divides voltage. It's a voltage divider, provides op-amp to work the single supply mode. This voltage divider is specifically for the second IC, which is the ICTL702. So here we have R7, 22.6K each, R7 and R8. So there's a wire going over here and coming here, and there's another wire going here and connecting to pin 2. Or else we can say that pin 2 is going all the way to pin 1, and this pin 3 is connected to this ground, and 5NF capacitor, which is connected to here. This is also at pin 3. Okay, so let's see. This C7, which is a capacitor at a value of 10 nanofarad, provides feedback. Okay, so this circuit itself is already made up of two low pass RC networks. So this C7 provides feedback. What type of feedback does that provides? C7 provides the feedback for shaping the response near the edge of passband and allows low frequency to pass through or filter out high frequency. So that is the function of this capacitor here. So V out will be passing through C8 here. So C8's main function here is to filter out any DC signal. Okay, so yeah, we have to calculate the FC here. So how is it calculated? First of all, we have FL, which is at 0 Hz, and FH equal to FC. The bandwidth, however, is equal to FH minus FL, which is FH minus 0, which is also equal to FH. So FC is equal to 1 over 2 pi square root R7 times R8 times C7 times C6, which gives us the 995.925 Hz, which can be rounded up and gives us the final value of 996 Hz. So basically that's the third stage of this circuit. Okay, so this is the final stage of my project. Final stage circuit of my project, medical devices. Yeah. So for this stage 4 final stage, it will be using IC3 LM386N-1. This is the only amplifier that drives current to power up the circuit. Okay, so it's going to be an audio amplifier that drives a speaker. No additional voltage divider is required because this circuit itself is designed to be working in a single supply mode internally. So this is an audio amplifier, by the way, as it's stated here. It's audio amplifier with single supply mode and drives current to speaker. Okay, so let's see in detail how does the current flow here. So here at this part, at upper part of the trimmer, there will be full amplitude. In other words, pin E has the full amplitude, while pin A and S has zero amplitude of the input waveform. So that's for the trimmer. So the current will pass through here, and this is going to be the IC here. So C15 is important as it filters out high frequency, which is frequency above 400 kilohertz. If we don't have C15, the output waveform will be slightly unstable. So we can see that how important C15 here, and it acts as a filter and also to stabilize the waveform as well. So this is C13. It's a capacitor. So this capacitor blocks out DC and allows AC to pass through as well. So in total, this is the only amplifier that going to directly drive current to the speaker. So there will be no voltage divider required, and that's all for the stage 4. So this is my complete analysis of the schematic diagram of this circuit, this medical device circuit. Thank you.